In this video, I want to talk about the idea of a normal distribution, which is a very common distribution that you'll find lots of data sets in the world. We're not going to go into too much depth about it. If you are interested in the normal distribution even more, I strongly suggest that you take a first-year statistics class, which goes into depth about the normal distribution and sees some very interesting properties of it. It's a very cool distribution. So in order to talk about that, the first thing I need to introduce is something called standard deviation. And we usually use the letter S to indicate the standard deviation. And just like the mean absolute deviation, it's a measure of variation, the measure of how spread out a data set is. If you remember from the mean absolute deviation, the MAD, so if we had n data points, x1, x2, x3, all the way up to xn, we calculated the average distance from the mean of our data points. And to make sure we were calculating a distance, we wanted it unsigned so negatives wouldn't cancel out with positives and we got a true idea of distance. We took the absolute value of each of these distances here. Standard deviation is similar, but instead of getting rid of the negative by taking the absolute value, another way we could do it is by squaring the difference. You can see down here, instead of doing the absolute value, we're squaring the difference. So instead of taking the absolute value, square each difference, sum them together, divide by n, so it's the average squared distance here. And then because we squared everything, we take the square root. So it's kind of the same idea as the mean absolute deviation, except instead of taking absolute values, we square everything, and then at the end, take the square root. Let's do an example to see how this works. So we want to find the standard deviation of the following data set, 2, 2, 6, 10. So the first thing I need is the mean. So let's calculate the mean. So we're just going to, of course, add together our data points and divide by 4. 2 plus 2 plus 6 plus 10 is 20. 20 divided by 4 is 5. So we know our mean is 5. Okay. So the standard deviation is as follows. So we're going to take each data point. The first data point is a 2. We're going to subtract the mean, 5. Square that difference and do that for each data point. We have a second 2. 2 minus 5 squared. We have a 6. 6 minus 5 squared plus 10 minus 5 squared. So we calculate those. We divide by the number of data points. There are 4 data points. And then at the end, we want to take, that's a poor looking square root sign, that's a little better. We take the square root of everything. So let's calculate this. 2 minus 5 is negative 3. Negative 3 squared is a positive 9. There is another 9. 2 minus 5 all squared is 9. 6 minus 5 is 1. 1 squared is 1. And 10 minus 5 is 5. 5 squared is 25. And this is over 4. And we take the square root of everything here. So let's add these up. We have 9 plus 9 is 18. 18 plus 1 is 19. 19 plus 25 is 44. So it's 44 over 4. And we want to take the square root of that. Well, 44 over 4 is, of course, 11. So this is the same thing as the square root of 11. And we know 11 isn't a square number, so we can't take the square root nicely, it ends up being an irrational number. And if you're interested, if you put it into a calculator, it ends up being around 3.32. We can say for sure, we know square root 9 is 3, square root 16 is 4, so we know square root 11 is definitely between 3 and 4. So if we don't have a calculator, we can estimate it like that. An important thing when we're talking about data is how extreme values are. And we need some sort of unit to describe these. And the best thing is a unit that is inherent to the data set. And that's what this standard deviation is. This is kind of the unit that you're measuring how far a data point is from the mean in. So we're thinking of our standard deviation of our unit that's inherent to our data set, because we don't want a value to change. For example, if we imagine we measured a bunch of heights, we don't want kind of a measure of spread to change just because we change the units from meters to centimeters or something like that. So it's really important to have a unit inherent to your data set. And the way we do that, of course, is in standard deviations. And this is the formula that calculates it. So we just figure out the difference between the point and the mean, so the data point and the mean, and then because our units are standard deviations, we divide by the standard deviation to tell us how many of those this distance is. Let's calculate a couple of examples, and we'll put them on a little bit of a graph, and we can kind of see what's happening here. So the first example, let me change my pen to black. My first example is going to be, suppose you have a data set that has a mean of, let's say, 10 and a standard deviation of 2. So what is the z-score? Of the data point, let's say 7. So let's calculate this. Okay, so we want the z-score. So we want to figure out the distance from our data point here to our mean of 10. So the data point is 7. And we subtract the mean. And we divide by the standard deviation, which is 2. 7 minus 10 is minus 3. So we have minus 3 over 2, which is negative 1.5. So that tells me that the data point 7 is 1.5 standard deviations below the mean. So on a little bit of a graph, if we have a mean of 10, here is, let's put some standard deviations in. So one standard deviation below will be 8. 2 standard deviations below will be 6. That's good enough for now. And I'll mark in what they are in terms of the mean and the standard deviation here. So this is just the mean. This was the mean minus the standard deviation. This is 2 standard deviations below the mean. And we can do that up here as well. So let's go 1 standard deviation up. So we'll add 1 standard deviation to the mean. So this is the mean plus a standard deviation. We'll even go 1 more. Here's 14. This is the mean plus 2 standard deviations. And this 0.7 Where does this lie? 7 is right here. It is 1.5 standard deviations below the mean. So maybe I'll mark that in. So this is 1.5 below the mean. So that's pretty cool. That gives us a nice picture of how this data point fits in our data set in terms of the standard deviation. Let's do one more problem. We'll use the same data set that has a mean of 10 and a standard deviation of 2. So what data point would be, let's say, 0.75 standard deviations above the mean? So maybe pause the video now and see if you can figure this out here. Okay, now that you're back, well, we know we want something that's 0.75 standard deviations above the mean, so that's our z-score. So that's our z-score here. Let's fill that in, 0.75. We're looking for the data point. We don't know that. We do know the mean of 10, and we know the standard deviation of 2. So we just have to solve this problem now. So we're solving for our data point. Here we knew the z-score, we knew the mean, we knew the standard deviation. Let's multiply both sides by 2. We get 1.5 equals x minus 10. Add 10 to both sides, just solving an equation. And we get that 11.5 equals x. So 3/4 of a standard deviation above the mean is 11.5. I'll do this one in green. So there is x bar plus 3/4 of a standard deviation, and that data point is 11.5. So that's kind of how these work. And normal distributions are very nice. They have very specific things you can say about them in terms of z-scores, in terms of standard deviations away from the mean. And that's what we're going to talk about next when I introduce what a normal distribution is. But before that, I just want to do one quick problem to talk about how you can use the idea of z-scores to determine how extreme a value is. All right, suppose that you wrote 2 tests, a history test and a math test. The history test had an average grade of 75 with a standard deviation of 10, and a math test had a mean of 70 with a standard deviation of 5. Your grades on both tests, an 85 on the history test and a 78 on the math test. Which test should you be more proud of your grade? Which test should you be more proud of? Or test grade, I guess. Should you be more proud of? So, the whole idea is, the farther you are away from the mean in terms of standard deviations, the more extreme the value. So, since it's on both of these are on the high end, they're extremely high, you want the one that's more extreme. So, let's calculate these. Let's do the history test first. So, the z-score is, well, we got a score of 85 minus a mean of 75 over a standard deviation of 10. So that's 85 minus 75 is 10. 10 over 10 is 1. So your score of 85 is exactly 1 standard deviation above the mean of the history test. For the math test, well, we got a lower grade on a test with a lower average and with a lower standard deviation. So let's see what happens there. So we subtract the data point minus the mean, and we divide by the standard deviation. So this is 78 minus 70 is 8, so we have 8 over 5, which is 1.6. So this guy's farther away from the mean because it's 1.6 standard deviations. And this is nice because you can compare grades of different tests in terms of this unit of standard deviation. Since this one is 1.6 standard deviations away from the mean, you should be more proud of your math test score. This is a more extreme value. So you can use the idea of z-scores to kind of help you determine how extreme various data points are. And in this case, being extreme is good because you're in the positive direction. So let's talk about this normal distribution now. And a normal distribution of a population, so you could be talking about things like weights of people or heights of people or lengths of fish or something like that. Any type of population. If you have something that's normally distributed, the histogram, if you took all of those data points of your population and put them in a histogram, it's going to look in a very particular way, and it's going to look like a bell curve, and the bell curve has a few properties that are very important. The first one, it's symmetric about the mean. So on either side of the mean, it looks the exact same. Also, within 1 standard deviation of the mean, you're going to have around 68% of your data. Within 2 standard deviations of your mean, you're going to have 95% of your data. And within 3 standard deviations of your mean, you're going to have 99.7% of your data. So let me kind of sketch what this looks like. So if we have our axis here, and we have a mean x, then I could draw a histogram with a bunch of bars, but that would take forever. So what I'm going to do instead is I'm just going to draw kind of a curve that approximates the top of these bars of our histogram. So I'll draw it and then I'll put in a couple of them just so you can see what's going on. So I'm going to draw this as best as possible. So I'm going to pause the video and try it a couple of times myself until I get a good one, and then I'll unpause it and you can see what it looks like. So that's not too bad. And what this curve represents, again, it's just a bunch, it's the top of the bars of a histogram, if you like. And I just don't want to fill up the entire graph with that. It could be really messy to look at, and all I really care about is the top of them to get kind of a feel of what's going on. But the key is these points up here. So I know, here's the mean, whatever the mean is. I know on each side of that, I'm going to have 50% of my data. And it's symmetric too. So however far we go on one side, the other side is going to have that amount of our data as well. So I know within 1 standard deviation, so I'll write it like this, and it's about here. So within one standard deviation, if I add a standard deviation and subtract a standard deviation from my mean, within here is going to be 68% of my data. So within here is, I'll do it in a different color, I'll do it in green, 68%. Which means, remember, this is a symmetric distribution and symmetric around the mean. So that means there must be, if there's 68% within a standard deviation on both sides, it must be split in two. There must be 34% on each side. Okay, and we can continue. We know that within two standard deviations, there's 95% of our data. So I know, let me put them in here, and I'm just going to say, instead of, just in terms of space, instead of saying x minus 2x and x plus 2x, I'll just put the plus, or this should be a minus actually. I'll just put the minus 2s here, and here I'll put the plus 2s. And so within here, do this one in yellow, within here is 95% of my data. Well, if there's 95% of my data between two standard deviations, see if you can figure out how much of your data is in these sections here. We know 34% is from one standard deviation below to the mean, and from the mean to one standard deviation above. Using kind of that same logic, see if you can figure out how much is in these two areas here. Okay, so, well, if there's 95% of our data in this area here, well, that means in 1/2 there is 47.5% of our data, since it's a symmetric distribution. So here is 47.5% of my data. I already have 34% of it. So 47.5 minus 34 is 13.5%. So this is 13.5% in here on the other side as well. And similarly, within 3 standard deviations, let me put another one here. So now we're 3 standard deviations above and below. I'll do this one in blue, I guess. So within here is, and I'll just write it, it's getting a little messy. I'll draw it a little better on the next slide. But within here is 99.7% of our data within 3 standard deviations of the mean. And playing a similar game to the previous thing, maybe pause the video and see if you can figure it out. How much of your data is going to be between 2 standard deviations below and 3 standard deviations below, and 2 standard deviations above and 3 standard deviations above. Okay, using the same logic as before, you should get that in here must be 2.35% of our data, and same in here. So that tells me out here there's only 2 regions left, more extreme than 3 standard deviations on either side. Well, if there's 99.7% within 3 standard deviations, there's only 0.3% outside, and it needs to be split in 2. So this is going to be 0.15% of my data outside of that down here, and another 0.15% of my data set down here, less than 3 standard deviations, and here more than 3 standard deviations. So let me draw this again on the next slide so it's a little less messy. So there is a better drawing of the data set here, what a normal distribution looks like. In fact, I'll label it normal distribution. So let's do a problem. So let's say we have a data set that comes from a population that's normally distributed. So let's say that we know that the lengths of a certain species of fish is normally distributed. So once we see those words normally distributed, we know lots about this data set. In fact, we know that everything up here holds, which is fantastic. And I'll tell you the mean and the standard deviation. So with a mean of, let's say, 35 centimeters and a standard deviation of, let's say, 5 centimeters. So, in a sample of, let's say, 1,000 fish, how many would we expect to be? And let's do a few of these. Okay? So I'm going to scroll down to give myself just a little more room. So the first one is going to be longer than 30 centimeters. Second one is between, let's do 25 centimeters and 40 centimeters. The third one will be between 40 centimeters and 50 centimeters. Okay. So, let's go up and modify our diagram a little bit so we can put in the mean here and the standard deviation, so we kind of can read off what's going on a little bit easier. So remember, we have a mean of 35 and a standard deviation of 5. So we scroll back up. So we know the mean here is 35 centimeters. And if we add one standard deviation, we get 35 plus 5, which is 40. If we add another standard deviation, so 2 standard deviations to the mean, we get 45. This one will be 50 centimeters. That should be a plus, actually. My mistake. That's plus 3 standard deviations, of course. And down here, if we subtract a standard deviation from the mean, we get 30. This is 25, subtracting another one, so 2 in total. And subtracting 3, we get 20. Okay. So, let's do part 1. So, part 1 says longer than 30 centimeters. So I'll do it in a few colors here. So let's do yellow for the first one. I'll just highlight it. Okay. So longer than 30 centimeters, that goes from 30 all the way this way. And I'll just put one line here just to kind of indicate that. So that tells me that, well, that's definitely the right half of the data. It's everything bigger than the mean, plus this section here, plus 1 standard deviation below. So what you can do, you can either add up all the sections, 34 plus 34 plus 13.5 plus 2.35 plus 0.15, but remember that everything on one side of a normal distribution is 50%. So in this half is 50% of the data. So I know that these definitely add up to 50%, and I just need to add this 34 here. So this is going to be 34% plus 50%, which is 84% of our data. But remember, we have our data is 1,000 fish, so we take 84% of 1,000, and that is, of course, 840 fish we would expect to be longer than 30 centimeters. Okay, let's scroll, do the same thing. Let's do between 25 and 40. I'll do this one in the color blue, I guess. So highlight blue just to remind us. Scroll back up between 25 and 40. So that is in blue here. We have here, so between 25 and 40. So it's those regions. So it is 13.5% plus 34 plus 34, so 68 plus 13.5%. Let's write that down. So that's going to be 34% plus 34% plus 13.5%, which is 81.5%, again, of 1,000 fish. And that is, of course, 815 fish we would expect to be between 25 and 40. All right, and finally, let's do between 40 and 50. So we scroll up, and we just mark it down between 40 and 50. So that is this region here. I'll do it in green, I guess. Maybe I'll highlight this. So I'll do this one in green. Scroll back up. Highlight. So that is between 40 and 50. That is there. So that is just 13.5% of the data is between 40 and 45, and 2.35% of the data is between 45 and 50. So together, that's going to be 15.85% of our data, just adding those together. So this is going to be 13.5% plus 2.35%, which equals 15.85%, and that's of 1,000. So we would expect 158.5 fish would be between 40 and 50. Obviously, it's not going to be exactly 158.5 since you can't have half a fish, but an expectation, it's fine to have decimals in it. So hopefully that gives you an idea of how the normal distribution works and how you can use it to solve some problems.